Or if you just drove up to Georgia, I wouldn't have to catch the ride back. Here in the morning, because that's a drive back. I mean, it's the same thing.
Have to drive here and then.
Oh, yeah.
Definitely.
What are we looking at, Dr. Harold?
Nothing for your eyes, pal, nothing for your eyes. Well, none of this is, none, you couldn't understand this stuff.
Right.
That's all I need is a few more ideas. All I need is a few more ideas. Well, you know, Malcolm.
Yes.
I know you're invested in it. It's like a labyrinth.
Why is it not telling me what I need to know? That did it, John, that did it. All right, so Domtar, tomorrow, meet here at 12 noon. All right, so meet here downstairs near the offices, right? Somewhere we'll be getting in vans, right? Let's see, we got 3 15-person vans, 15 passenger vans, I guess. I guess that 15 includes the driver, but still, right? So we got 3 vans. There probably will not be 3 vans of us, right? But we got 3, so we spread out and do that kind of stuff. So see how things go. Questions or comments? Let's see. Work attire, appropriate work attire. A work attire like you would like to present yourself to them as a engineer, as someone who would like a job sometime in the future, as a representative of Milligan University, so you don't need to be, definitely no ties, definitely no super crisp shirts, that kind of stuff, but you want to look good, you want to look decent, you want to look like you want a job, whether you want a job or not. I want you to look like you want a job. I want you to act like you want a job. I want you to be ready to take a job, whether you want a job or not. Okay? If you don't want any of that stuff, then don't go. Okay, right, on the trip. Because this is our first impression to Domtar. Okay? This is the first time we've had any kind of contact with those folks, and we need to make it a good contact. All right? Because whether you want it or not, other folks do want it. Okay? So, I'm trying to be serious here. Right? Make sure you come approach. Now, we may talk to the lowest level of the HR manager's department and have no real contact at all. Okay, that's the way things start. All right, so we may be talking to the chief engineer. I have no idea. So we need to go in like we're professionals and like we know what we're doing and like we want a job, whether you ever want to work in a paper mill or not. Now, the other side of the coin is this is a great field trip. Pulp and paper mills, fantastic engineering stuff from every single aspect of it, from machinery, mechanics, strength of materials, maintenance, life cycle costing, thermal fluid sciences, heat, power, cogeneration, burning wood. I mean, it's just chemical, chemistry, just everything. It's every single thing in the pulp and paper mill. It's old school all the way up to brand new modern, systems and controls, PLCs, sensors, all kinds of stuff, right? So it's pulp and paper. It's a very cool place to be. So hopefully we'll get to see a whole bunch of stuff. I know we'll get to see a lot of stuff because you can't walk by the place without seeing a lot of stuff. So be excited about it if you're going. If you're not going, have fun, whatever else you're doing. All right. So we'll meet downstairs near the offices at noon to leave at 12:15 so that we can be in their parking lot parking and doing our stuff well before 1 o'clock, which 1 o'clock's what time we're supposed to be there. So that's the game we'll play. We suspect we'll be back here before 5 o'clock, but there's not a guarantee on that. So if you've got time constraints, time limits that are going to force you to not be able to meet that, then I'm sorry. You'll just have to not go. There won't be an opportunity for us to be touring somewhere and somebody stand up and say, "Hey, I got to go." Once you're in, right? And we're doing our thing. So let's see, favorable attire. Required attire. Let's do that. Required dress, right? Would be substantial footwear. That's the buzzword, the code word, right? That you use, and what that means is no open toes. Full shoes. They can't, the minimum shoe that you could have on would be tennis shoes. That would be the minimum. If you show up with less substantial than tennis shoes, you can't go. Right? That's just the way. And it's not like, well, we'll try it and see if we can get in. No, we're going to look around and go, okay, Keith's got on Caswalker Street Burners, that'll work, right? That'll be okay. Malcolm's got on sandals. Nope, can't go Malcolm, right? That kind of thing, right? That'd be the game. So tennis shoes, what Lauren's got on, what Keith's got on, what Josh has got on. Josh has got on more substantial footwear than Keith. I'm just letting you see, right? Richard's, Richard, you can go, but that's the minimum you go with, right? That kind of stuff, right? Next minimum, long pants. Next minimum, at least elbow length sleeve shirts. Okay, if you so there. Those are the minimums that are going on now. Preferred would be boots. Preferred even more than boots would be steel-toed boots. Don't have to have them. If you don't have them, don't go out and get them unless you want them. Okay, but steel-toed boots and natural fiber clothing, wool or cotton. That's the two that can get you places, right? Wool or cotton clothing. long sleeves. Those things can potentially get you into a better tour, okay? If you don't have them, you're not gonna get kicked out, you're not gonna get to not go, anything like that. But what happens very often, and what happened last year at John Sevier Combined Cycle Plant was, hey, who's got safety shoes? Who's got steel-toed shoes? Oh, I see you. Yeah, you got long sleeves, you got on long pants and steel-toed shoes. You folks come with us, we'll go on the more, bigger, better tour. Okay, the rest of you folks, you'll go on the other tour, right? And that may not happen. That may not happen at all. That's a common thing. That's not just at John Sevier, right? That's a common thing at industry, right? So if you want to potentially get further in, then it may be that we have one tour guide and that we don't have an opportunity to split off and do that. So, okay, you're wearing steel-toed shoes, no big deal, right? Okay, so there. Let's see, other questions, comments? All right, there you go. It's good. It's a good field trip. So it's a really good field trip, really good exposure to heavy industry, to real machinery, real equipment, real thermal fluid sciences stuff. So, so there. All right. Other questions? Yes, John.
Is this would they prefer we don't take pictures of things?
They will probably not allow you to have they may make us put our cell phones in a box to go in, right? Yeah, it's good. It's a good point. Do not take a picture. Don't. Do not at all. If they allow us to take pictures, I'll be surprised. Okay? If they do allow, then you got to follow the rules, whatever rules they provide. And so, yeah, do not get me in trouble, or you will be in trouble, right? You know, kind of thing. You know how that goes, right? Yeah, good question. Yeah, you know, if you're tempted to go, oh, that'd be so super cool. Let me just grab my phone and take a picture. Not unless it's approved. You know, not unless we are allowed to. So, and that'll be loudly announced. And I am almost certain the answer is no. Okay, you know. So, yeah, good question. Other comments, questions? All right. Good opportunity. Homework. We had homework. Oh yeah, we had steam turbine, didn't we? Excellent. Yeah, we had maybe more than one steam turbine. Yeah, cool. All right. So how'd you do? What were we asked here? Determine the power output of the turbine. So, what kind of turbine power did we get? That's where you guys talk to me.
1,078 kilowatts.
78 kilowatts. So I meant to fire up ref props. Anybody got ref props fired up? I intended to fire up ref props and I didn't. I think 1,078 is what I got, something like that.
That's also what I got. So
Very
that
good.
should be concerning to you.
That's also what I got. So
Yeah.
they're all very wrong.
I got 1116.
Never mind, we're right. Keep going.
I know the wrong answer, everyone's fine. Oh my.
Sorry for that delay. So how did this happen, right? So, we've got multi-stage steam turbine rated for 5 megawatts, maybe not doing 5 megawatts, 7 turbine stages. That stages, right? That just means blades, or nozzle to blades, nozzle to blades, nozzle to blades 7 times, right? So 7 of those. Well, we've got a flow rate, so mass flow rate inlet is 50,000 pounds per hour. Inlet steam conditions, 400 PSIG and 700 degrees Fahrenheit coming in at the inlet of the turbine. Exit conditions are at the exit is 150 PSIG. And we're given a temperature. T at the exit is 530 degrees Fahrenheit. So, if this steam is superheated, then we've got two independent properties, and we can get everything else. Right? We can get enthalpy at the exit, entropy at the exit, specific volume at the exit, whatever internal energy at the exit gives free energy at the exit. We can get whatever we need. The exit, if this is superheated steam in, then pressure and temperature in allows us to have enthalpy at the inlet, entropy at the inlet, other things at the inlet if we're interested in those other things. Determine the power output, determine the stuff around this turbine. So I'm going to say dmcv dt summation m dot I minus summation m dot E. And I'm going to call this steady state, steady flow, which that equals 0. And I'm going to say one inlet and one outlet. M dot I is M dot E. It's 50,000 pounds per hour of steam flow. Then I'm going to say dE CV dt. And sorry, my control volume is like that, right? Kicked around the turbine is equal to heat transfer for the control volume plus summation m dot I hi v squared I over 2 gzi minus summation m dot E he v squared E over 2 E minus power of the turbine. Same song and dance. I'm going to say steady state, steady flow equals 0. For my steam turbine, I'm going to call heat transfer negligible. I'm going to say for my turbine, for this turbine, there's one inlet and one outlet. For this turbine, I'm going to assume changes in kinetic energy, changes in potential energy are 0 or negligible. And so I'm going to get the power of my, let's do this, the power for the shaft, right, is equal to mass flow rate entering the turbine, because m dot I equals m dot E, so mass flow rate entering the turbine, and throw that over there and we say HI minus HE. There's the power equation for the turbine. So I've got this. If I could just know these other things, I could get more information, more data, more understanding, and we can know those things from ref props. And ref props would tell me 700 Fahrenheit, 400 PSIG. And then ref props would tell me 150 and 530. And so enthalpy in is 1363.0, 1289.4 output. So there and there, all that's known through the unit conversions and stuff. And I came up with something. What did I come up with? I came up with 1075.8, but I didn't use ref props. I used Herald props, which is better. So, but yeah, same kind of number, right there. Yes, Levi.
Didn't you just send us your props? Making me buy this program, not even good.
Couldn't handle Herald props.
Because you made that all in Excel, right?
Yeah.
All in,
Yeah.
what's the size of that Excel?
Oh, I don't know, probably 75 megabytes or so. So not that big.
That's pretty good for Excel though.
Yeah. Does all right. Well, what else were we asked to do? All right, that wasn't it. Of course, this one didn't turn out to be that bad, right, at all. But the other thing was, what's the isentropic efficiency of the turbine, right? And for A turbine, let's do it right here, isentropic efficiency is the real power produced divided by the isentropic, or the perfect power produced. Real power, where could that come from? What could that be? Ah, there it is, right? This is it, that's the real power produced by the turbine shaft. And so, we could say M dot I HI minus HE real divided by M dot I HI minus HE isentropic. We could use that number and then put mass flow rate and enthalpy differences down there. Or we could just say, hey, same mass flow rate through a real turbine as through a perfect turbine. Same inlet steam for a real turbine and a perfect turbine. So what was that, 1,380 or whatever we saw on ref props. Let's see what it was on ref props. 1,363, sorry. 1,363, 1,363, 1,289.4 is what this value is. Now, if we could just find this value, everybody would be happy, right? And so how do we find this value? Well, a perfect turbine and a real turbine have the same exit pressure. A perfect turbine would relate to the second law of thermodynamics. CB equals summation over all the spots. Heat transfer for all the spots